Greetings, everyone. My name is Daniel Wilson. I'm a PhD candidate at Liberty University studying under Dr. Wayne Strasser in the Fluid Research Group. Today I'm going to be talking about a banana puree wave cycle in a twin fluid atomizer. Hopefully we'll have some fun and you'll get to learn a little bit along the way. The objective of this research is to use computational fluid dynamics, CFD, to characterize this banana puree wave cycle in a novel twin fluid atomizer. Now you might be asking yourself, why banana puree? Well, we're interested in atomization of highly viscous non-Newtonian fluids, and banana puree is both of those things. Some applications for these sorts of fluids are manure slurry atomization for energy conversion and fertilizer production, and also gelled propellant atomization for aerospace. Viscosity is important for atomization processes because it drives droplet size and is a retarding force for atomization. This wave cycle becomes very important for atomization of viscous non-Newtonian fluids. So we want to elucidate mechanisms and instabilities surrounding this wave cycle in this atomization process. This is the wave atomization process where these waves form that we want to study. It combines a unique atomizer design with a viscous non-Newtonian liquid to produce what we call wave atomization, wave augmented varicose explosions. You can see an animation of it in the middle of your screen there. So the atomizer design has a central gas flow instead of an outer gas flow. This is the opposite of a standard twin fluid atomizer design. It also has a wave-inducing inner design, so those waves rise up into the steam flow, and that's important for the atomization mechanisms. We use banana puree as our non-Newtonian fluid. It's shear thinning and temperature thinning as well. And then we call it wave augmented for the waves inside the nozzle, varicose because of that bulging liquid that you see, and then explosions occur periodically in the radial direction. Our computational approach involves a 90-degree wedge model with periodic boundary conditions. We add a porous media section in the Puree annulus to create a larger pressure drop and simulate a longer piping system. We use the Herschel-Bulkley model for Puree viscosity, and we model the steam flow as compressible. At the bottom of the screen, you can see the solution methods in ANSYS Fluent, including turbulence model, discretization schemes, time step, etc. On the right, you can see a snapshot of the mesh. This is the 90-degree wedge mesh. We took a base mesh and refined it 3 times in the atomization domain for a total of 132 million elements. So we have this wave-inducing atomizer design, which you see on the left, with the central steam flow, annular Puree flow, and these waves form inside the nozzle. On the right, you can see a snapshot from a CFD simulation of a wave rising up towards the nozzle exit. Keep this frame in mind as we'll see it on the next few slides. The top of it is the nozzle axis center line. So these are non-Newtonian, annular, high blockage ratio waves that form in a highly periodic cycle. Here's an overview of one wave cycle, one sample wave cycle. First, in frame 1, a new wave rises out of the wave pool. Now in frame 8, you can see how we label wave pool and beach. This is just simple, straightforward terminology. So a new wave rises out of the wave pool and continues to rise through frame 4, and 5 is where it really peaks at the nozzle exit. Then it starts to collapse. You see that radial bulge form at the bottom. And then finally, as it completely collapses, a new wave rises in its wake. And this process continues to repeat about every 0.001 seconds or 1,000 hertz frequency. Here are some important wave parameters as we look at this system. As far as geometry goes, we have the beach to pool ratio at 0.4. This is something we're interested in altering to see how it affects wave formation inside the nozzle. Wave angle is about 50 degrees at the peak before collapse. That's relatively high for a wave. The blockage ratio is high at 0.5, 50% at the peak before collapse. The wavelength is measured as shown on the bottom figure on the screen there. Since we don't have wave trains, but with just one wave forming at a time, we decided to measure it from the peak of a just forming wave to the center of that radial bulge outside the nozzle. We find the wavelength to be about 0.7 nozzle diameters, and over 3 sample measurements of this wavelength, we found the coefficient of variation to be 0.57%, very small, so this is a highly repeatable wavelength measurement. Two important dimensionless numbers are the Weber number and the Reynolds number. Weber number is inertial effects to surface tension, and Reynolds number is the ratio of inertial effects to viscous effects. If we compare these to free surface water waves from the literature, we see that Weber number is an order of magnitude higher and Reynolds number is an order of magnitude lower. This highlights the greater inertia of these waves compared to free surface water waves and the greater viscosity because of the thick banana puree. What mechanisms are at play in this wave cycle process? Well, first, for wave formation, Kelvin-Helmholtz instability is dominant. The puree flow, as it's pushing into the steam, deforms the surface at the wave pool. This causes streamline deflection and sheltering. And I should back up and say that the animations on the right, which you're seeing, top is velocity vectors, bottom is pressure, white is high, black is low for the pressure, and that puree interface is being outlined there so you can see how it's moving through the domain. So you can see the streamlined deflection clearly in that top animation, and the sheltering there in the bottom. That accelerated steam flow is going to lift the puree as velocity increases, pressure decreases, creating a lifting force. And this is the Kelvin-Helmholtz mechanism where pressure gradients are induced to lift that wave out of the wave pool. Note too, as the wave continues to rise, the exit area closes off, steam accelerates even more, creating more of a lifting force. You also get shear thinning at the wave crest from the steam shear, which causes further acceleration, and the steam behind the wave on the windward side compresses. This increases temperature and pressure. The increase in temperature reduces the viscosity even further for acceleration. As the wave moves across the beach area, it experiences friction at the wall that wants to make it trip over, so to speak, and you start to see that pressure propagate through the wave to produce that radial bulge. And eventually the pressure just overcomes the inertia of the wave and it collapses down. We can also observe the time averaged effect of the wave. Here you see contours of Mach number that are time averaged. And it's clear that the exit area is reduced, producing a nozzle effect. We've got the vena contracta labeled there, that's the pinch point, and the steam is accelerating from just Mach 0.2 at the inlet all the way to transonic speeds. This means it also goes from incompressible to compressible. The vena contracta is labeled with that black dashed line, and the solid line is the Mach number profile at that point. Here are a few takeaway points to wrap up this presentation. Our objective was to use CFD to characterize this banana puree wave cycling in a novel twin fluid atomizer for viscous non-Newtonian atomization. We saw a high blockage ratio with annular waves producing a radial burst at 1,000 Hertz frequency, an extremely consistent wavelength. For wave formation, Kelvin-Helmholtz, steam acceleration, shear thinning all contributed to the wave rising and growing, and then friction and pressure buildup contributed to wave collapse and that radial burst. The time averaged wave causes the steam to accelerate from Mach 0.2 to transonic speeds. We also studied mesh independence, but haven't shown that here for sake of time. In the future, we'd like to look at the effects of geometry changes on these wave cycle characteristics. Thank you so much for your attention, and please reach out to me with any questions.